Welcome to our Lecture 7, Part 1. In this section, we'll show you how to do multiple logistic regression with R, and I don't think you'll be surprised because it's a logical extension of simple logistic regression that we looked at before. So I'm going to be working off the obesity, risk, and sex and other predictors data set from NHANES data from 2013 to 2014. I'm just going to read this in again, set my working directory, read it into an object called NHANES SO. And just look at what we have here. The names, some of the things we have in here include their age in years, their BMI, their systolic blood pressure, their HDL measurements called LBD, HDD, and I haven't changed the names of these because I wanted to make a point that sometimes when you get data from national or international databases, there's a coding thing that you'll have to go back to the code books and look at, and so I put a link for a code book here. Ultimately, if I were working with these data myself, I would probably rename these to be more intuitive. So just let's remind ourselves of what we did before. I'm just going to set things up again. This gender, I had no idea which was a 1 and which was a 2, which biological sex was a 1 and 2 until I went to the code book. Turns out those coded 2 are females, those coded 1 are males. I created and added to this NHANES O object another column called female, which was a 1 for females and a 0 for males, and I just created that by taking the value of the gender variable and subtracting 1. So those that were 2s, the females, when this new variable female would be 2 minus 1 or 1, and those that were previously 1s, the males, would be 1 minus 0 or 0. So we'll put this in. And we're going to be working with obesity as our outcome again, and the BMI info was only included for persons who were over 18 years of age. So I just wanted to get a subset of that group, and also among those who are over 18, those who are not missing their BMI. So let's just look at how many people we have in the data right now. I'll take a length of the gender column, but I could take a length of any of the columns in this data frame NHANES O. And there's 10,175 observations, but that includes a lot of people who are less than 18. So I'm going to take a subset, I'll call it NHANES OS for subset, which is a subset of my original data frame NHANES O. It includes those that are not missing. Remember, this is the syntax is.NA comes back true if the observation is missing, and false if it is not. And I want those that are not missing, so those that are not true on the query is.NA for the BMI measure. And I want to couple that with people who are over 18 years old. So the column for age in this data is called RID age year. So they're going to take a subset of the original data frame to include only these folks 18 years and older who are not missing obesity. And that reduces the size of our data set to about 60%, 5,847, when we got rid of the younger folks. Now we have to, and this is what we did before, but I'm just reminding you so that it doesn't come in as unfamiliar, is we had to create an indicator of being obese, and by the norms it would be those who have a BMI of greater than or equal to 30. So we created a column in NHANES SOS called obese. We used the if-else command and said, well, if NHANES SOS, the BMI column, is greater than or equal to 30, give the obesity indicator value 1, else, if it's not, give it a value of 0. And so we should have values for do that again here, and we have the 5,847 values. We haven't added or taken any away, so that makes sense. And then we went through and did some regressions, and I won't go through these in detail, but this is the simple logistic regression. The first one we did on obesity on female. We used the GLM command. Obese was the outcome, female was the predictor. The data set was NHANES SOS, and remember we have to tell it the family the outcome is binomial, and the link we're using to relate the outcome, the function of the outcome, to the linear combination of our intercept and slope is called the logit function. That's the log odds function, and this just gives us the results. If we use the coef and confinf commands and exponentiate the results, we get things off the log scale and onto the odds and odds ratio scale. When we went to HDL, it turns out there were 274 persons missing HDL, so to make things easier to work with, I resubsetted that original subset of those greater than or 18 who had BMI, and I removed those. I only kept those that were not missing HDL cholesterol levels. And so now what happened here was now the remaining data we have to observe is and used for fitting models is we have 5,573 observations when we got rid of the 274 who did not have an HDL cholesterol level. This is the simple logistic regression of HDL cholesterol levels. The predictor obesity is the outcome, and you could run this and verify. We've already shown this in the lecture on simple logistic regression, and we re-showed this in the lecture on multiple regression. So I'm just setting things up. The next thing we did was categorize age into 4 groups. Remember, we had to use that library called GTools. You had to load that package into your R library, and then we have to pull it into our session using the library command. And then we cut age into, we created a column in our NHANES SOS data frame, the one we're working with called AgeQ, which was a factor variable putting age into 4 quartiles. We used the function called quantcut. We told it to cut age year into quartiles such that we got indicator for 0 to 25th percentile, the 25th to 50th, the 50th to 75th, and the 75th to the 100th. So in those 4 quartiles, and then we just simple logistic regression of obesity on those quartiles. So now let's do the multiple linear regression, multiple logistic regression, so that we can relate that final model we showed in the lecture, obesity as a function of sex, HDL, and age quartiles using this NHANES SOS data. All we have to do is we can still use the GLM command. Obesity is still our outcome, but now we just put in the predictors of interest in additive format. We want to take sex called female plus HDL plus age quartile. We're pulling this again from the data frame NHANES SOS, and the family of our outcome is binary or binomial, and the link that we're using is we're relating the log odds of this outcome, the logit function, to the linear combination of an intercept, a slope for sex, times sex, a slope for HDL times HDL, and a slope for age quartile indicators. So slopes for the age quartile indicators. Do the summary of this. And you can go up here and you can see that we get our intercept estimate of 0.87, our slope for sex, female of 0.78, our slope for HDL of negative 0.044, etc. Maybe easier to read this if we applied the coef function to this multi-linear logistic regression object. And it just puts it as a numeric vector, and we can see all those things there. If we wanted to get the resulting odds for the reference group with all x's 0 and the odds ratios, the adjusted odds ratios for each of our predictors, we could, because the slopes are on the log odds for the intercept and the log odds ratio scale for the slopes, we could just exponentiate the coefficient function applied to that object to just exponentiate this numeric vector. If we do that, we get our starting odds for this model of 2.38, and then the adjusted odds ratio for sex, 2.18, that I rounded to 2.18 in the lecture, the adjusted odds ratio for HDL of 2.957, and the adjusted odds ratios for each of the age quartiles as well. We could also get the confidence intervals for the starting odds and odds ratios by exponentiating the confidence function applied to MLR to the objects. If we just did confident, we would get 95% confidence intervals for the intercept and slopes on that log scale. If we exponentiate it, we can get these confidence intervals for the respective odds for the estimated by the intercept and the adjusted odds ratios by the exponentiated slopes. Just show you something. If we wanted to do prediction with this, like if we wanted to estimate proportions, for example, of obesity for different groups, how could we make this a little easier than just doing it flat out by hand and just using R as the calculator? Well, I'm going to do something that we did before earlier in the course as well. I'm going to store the results, the coefficients, that numeric vector of coefficients. I'm going to store it to an object called beta. So I'll call this beta, and I'm going to apply the coef function to MLR2. And if I do this, and then let me just type beta and show you what it is. It's simply that coefficient vector we looked at before. And recall, I can access any one column. This is one row. These are the row names here, and then one row of values. I can access any column by typing the object name, and then in square brackets, its column number. So if I want the intercept, I can type beta, and then in square brackets 1. If I want the slope for age quartile 4. I can type beta and then in square brackets, that's the sixth column of this vector, so I would get that. So I can still use R as a calculator, but I don't have to hand type in the numbers, and I can actually get it to do the computations for me without me actually typing in the coefficients, etc., if I pull them from this beta object. So if I wanted to estimate the proportion of females with HDL of 75 who were 65 years old and hence in age quartile 4, the proportion who were obese, I could estimate the log odds first by just taking the linear combination, the appropriate linear combination of the intercept and slopes and x's from this model. So I would take the intercept, which is the first column of that beta object, plus the slope for sex, which is the second column of that beta object, so beta square brackets 2 times 1 because we're looking at females, plus the slope for HDL, which is the third column of that beta vector, multiply that by 75, the value for the group we're looking at, and then because they're in age group 4, the only indicator activated for age quartiles is that for age quartile 4, that's the fifth X and the sixth beta column in our beta object, so I would add that. Technically I'm multiplying it by 1, and just to be consistent I will do that. And what I'm storing in this, I'm storing this in a number, a scalar called ln odds 1, for the log odds for this group. And if I look at this, it comes out, it's negative 1.197, close to what I showed. I rounded for my hand computations, so the results will be slightly different. The nicety of this is it doesn't round, but it takes these all out to their multiple decimal places in doing this. If I exponentiate this to get the odds, I get odds of 0.302, very close to what I showed. Again, my answers will be slightly different in the lecture because of rounding. And then to get the proportion of probability in this group that's breastfed, I take the exponentiated log odds, the odds, divided by 1 plus the odds. Do that. And we get an estimated proportion of 0.232 as opposed to the 0.234 I showed in the lecture. We could also do this for the other group we showed, males with HDL of 85, age quartile actually 3. So if we do their log odds, I call this log odds 2, it's the intercept beta square brackets 1 plus the slope for sex beta square brackets 2 times 0, since they're males. Their HDL is 80, not 85, plus the slope for HDL of that beta of that column 3 times their HDL of 80. Plus the fifth column, which was the coefficient or slope for age quartile 3. We do this, we get the log odds for this group of negative 1.92, very close to what I showed. Again, I rounded. We could get the odds for this group, 0.1468. We could estimate the proportion. We didn't show this, but we could do this now. The proportion of children in this group, proportion of adults in this group, males the HDL of 80 in the third age quartile who are obese, by taking the odds for this group divided by 1 plus the odds, comes out to be about 12.8% compared to the 23.4% we got for the females. And if we wanted to get the estimated odds ratio of obesity for the first group, the female HDL 75 in age quartile 4 compared to this group of males with HDL of 80 in age quartile 3, we could take the odds, the exponentiated log odds for the first group, and divide it by the exponentiated log odds for the second. And that gives us that odds ratio of 2.05, slightly different because of rounding what I did, but exactly the same concept.